about telephony products and Kubernetes and why they're so hard. Do you have a power? Are you just going to keep pushing things?
Just going to blame Windows 10 for that.
Okay, that's probably not got power plugged in. Okay, over to you anyway.
Batteries to last. Okay, so this is really a bit of a war story talk. I'm going to tell you a bit about what we did and what went wrong. I've given this talk twice. This is to an audience of people who have some idea what containers are, but probably don't know anything at all about telephony. I've also given it once at Metaswitch, where it's the exact opposite. So I'll skip over some slides that explain what Kubernetes is and stuff like that, because you probably have heard of it. But bit of context. So I work for a company called Metaswitch. We do telecoms and networking software, and the typical customer, actually not the typical customer we care about is a large telecoms company. You know, AT&T, Deutsche Telekom, BT, one of those guys. They're running their own network and they're running telephony services over it. Over the last few years, things have changed a lot. I'm going to talk a bit more about this, but virtualization is just turning hardware sales into pure, means that instead of shipping hardware with our software on, we're now shipping pure software, much more, become much more of software only, having gone a little bit into hardware. And now we're moving some of our new development into containers. And this entire talk is caused by me having said, surely our existing products just run in containers. Spoiler alert, not really. So I'm going to start with a little bit of history. This history is important because it makes you understand where all the pain come from, because most of the pain is actually self-inflicted, as all pain is. But this is the history of telecoms. So we start off with lots of pretty young women being paid almost nothing to sit in an office, being shouted at, plugging cables across, and that kind of worked. And then they invented automatic switches. I don't know if any of you guys have ever seen a telephone switch, but they are very, very, very large. Think something as big as a shipping container full of electronics. When you go around a modern central office, there's lots of free space because they've got rid of lots of those and replaced them with those. That's appliance hardware, otherwise known as, well, it's a server, isn't it? Nothing much more to it than that. It's a server running some software. And one of those in a rack will replace more than one of the big, massive, room-sized telephony switches. And now we're moving on to this. Now, this is a step of progress in the same way that Donald Trump is the step of progress of the human race. It's all gone a bit wrong at this point. We're gone to virtualization, and they came up with this thing, NFV, ETSI, Mano. And yes, I have started talking acronym language. Just ignore that. It happens. Have any of you heard of any of those acronyms? Yeah? Okay. I see a few people nodding. You have my sympathy, but not much, because I've had to read all the specs. So what's all this ETSI, Mano stuff about? I should say what NFV says. Almost none of the other acronyms actually matter in terms of what they stand for. NFV is Network Functions Virtualization. It's the idea of taking network capabilities like running telephony systems, switching, all the rest of it, and moving it into virtualized environments, running it in VMs, containers, whatever. And all I'll say about that picture is, gosh, there's a lot of stuff on it. What kind of features has ETSI, Mano got? Well, it was going to be the great new thing that will fix all your problems. It's a standards-based approach. It's lots of features. It'll do deployment creation and healing and scalability, and all the telcos thought it was great. But actually, firstly, there are a lot of acronyms. The whole thing, another little bit of a war story. This is actually true. We had a customer that we were shipping some of our products to, and before they would deploy them in their lab, they insisted we rename them so they all had 3-letter acronyms, because they weren't capable of coping with products that didn't have acronym names. Calling them by something you can pronounce is out. The telcos like acronyms. The ETSI Mano specs, I haven't read all of them because there are easily 1,000 pages of them. Maybe several thousand, I don't know. I kind of lost track. There are dozens of PDF files. Many of those PDF files are over 100 pages long. Some of them are several hundred pages long. They're utterly impenetrable. They're very vague because so they say things like, maybe you should do this, or alternatively you could do this, or you could do that, or you could do the other thing, or maybe you could do something else. Well, great, thank you. That's not what a standard's meant to be. And the whole thing's very immature. It's not, ETSI Mano doesn't really exist yet, and it might never really exist. I mean, it might be possible that they never really managed to get this all working. What really happens is telcos do what they might have done anyway, and then they use all these acronyms to refer to it. So that went well, didn't it? So Why such a mess? Well, you can kind of imagine it's a bunch of telcos, right? There's too many cooks involved. All the vendors got to write bits of the spec, so they all wrote a spec that said, our product does X, so we'll write in that you should do X. So you then have 100 vendors that do that. You've got 100 different examples of how it will work, which means you can do any damn thing you like and it'll be consistent with one of them. Lots of legacy applications for that. Telcos are mad for acronyms. I told you the little acronym story, 1,000-page docs. They love that stuff. They think it means they're working really hard. And they have people whose job it is to read and write these specs, keeps them in work. Systems integrators loved it to be complicated because that's all their money. Nobody's any incentive to make it easy, and it's a total train wreck. So that's all gone a bit wrong. And the telcos have woken up to the fact that this thing that they were sold that would solve all their problems not only hasn't solved all their problems, it's given them a whole bunch of new problems they hadn't thought of. So that's not going very well for them, and they are trying to figure out what to do next. So, surely somebody must be deploying large, complex, scalable systems and not making a total dog's breakfast out of it. Let's leave the telcos aside for the moment. We can all think of companies. Amazon, Google, Netflix, they all run big, complicated networks. They all run complicated applications across those networks. Many of them do things like telephony. Look at Google Hangouts, look at telephony streaming, look at Netflix streaming movies. Both of those are doing similar things to telephony to some extent. So it's clearly a solvable problem that other people have solved by the extremely important point of not being a telephone company. So let's just pinch what they're doing. Let's go for what works. People like Kubernetes. Let's just do it. It's going to be great. What could possibly go wrong? Spoiler alert, rest of the talk. What is Kubernetes? You probably know this. This is for the guys I gave it to at work. It's originally a Google project, containers, orchestration, management tools, deploys lots of environments. Industry standard, well, it's one of them, but it's very commonly used, obviously. So you kind of knew all that. Is it any good? Yes, actually. If you've ever tried to use OpenStack, Kubernetes is just this beautiful breath of fresh air. It's not like stabbing yourself in the eye with a fork. It does hurt sometimes, but it's, oh. And we got Clearwater, which you guys won't have heard of, so I should have mentioned this. It's one of our applications, which I'll talk about, maybe mention later on. We got it running from, basically it'll run in, we can spin up a container and manually network it to, it'll run in Kubernetes. Got that running in Kubernetes in a couple of days, and that's from having never installed Kubernetes. I'm thinking, well, great, this is going to be really easy, right? Dead easy to install. You can just crank up any one of the standard installs and it works. All the basic features, healing, scaling, and upgrade actually exist. And it's worth saying that we have all the stuff about Etsy Mano, people have been working for years. Millions and millions, if not billions of dollars have been spent on it. Most of the orchestrators can't do healing yet. It's, you know, it is that stalled. Whereas Kubernetes just comes along and it's got all that stuff already. And it's just a better developed project. It's got developers who are focused and they're more effective, and it's not like OpenStack. If there's anyone here who likes OpenStack, please don't beat me up, okay? Just so we're going to throw Etsy Mano in the bin as an idea, and we're going to press on and we're going to do OpenStack, and it's going to be great. Sorry, we're going to do Kubernetes, and it's going to be great. So here is our plan. You've probably picked up by now, but the most fun I get out of giving these talks is the fact that it gives me an excuse to spend a couple of hours on Google Images. So what can we show for MWC? The context here is that MWC is Mobile World Congress. It is a very, very large conference. It was held in Barcelona this year. It's just gigantic. If you've ever been in Terminal 5 at Heathrow, it is several times bigger than that, full of telco exhibitors. Gigantic. Big, big money around. So they were going to try and show off a solution at that, and I was going to do a demo of this. And most of the rest of the talk is stuff we discovered along the way. So what we're going to do is a full Vultee solution. I realize none of you have any idea what I'm talking about, but that's fine. Next slide will explain that. It'll be running under Kubernetes. We'll use the native orchestration tools and management. So for management applications, we're not going to use some fancy telco thing. We're just going to install Grafana and look at some graphs, things like that. We're going to put some load through it. We'll do some stuff on a mixture of AWS and on bare metal to show that you can run it anywhere and keep everybody happy. And there's a disaster recovery scenario where we're going to have failover between the two clouds. Surely that's not too demanding. Yeah, well. Vultee solution. I put this slide up because It just gives you an idea what my life is like, frankly. I doubt anybody in this room has any idea what any of these things are. So I produced another version of this slide in which I annotated them all. So the VoLTE solution, VoLTE is 4G mobile telephony. Telephony, well, as you know this, 2G was voice, 3G was data, 4G was better data that you can also run voice over. And gradually the mobile phone companies want to start moving everything onto the 4G network so they can take their 2G and 3G networks and scrap them, free up the spectrum and make more money. And VoLTE is how they do it, voice over LTE, and it's got a lot of different pieces. Fundamentally, what is happening underneath this is phone calls, right? Pick up your mobile phone, call your mother, that's going through VoLTE. It is doing all the stuff, routing the call, billing the call, all the rest of it. But to give you an idea of the sort of complexity and mess that is involved in that, we're not providing a full VoLTE solution, by the way. We're providing most of the pieces of infrastructure that a telco wouldn't already have themselves, because, for example, a customer database they would have themselves. So we've got Perimeter SBC. An SBC is essentially a smart firewall that understands about different telco networks. So it understands that network A can talk to network B, but network B cannot talk to network C unless you've authorized in method X. And it will do things like denial of service, protection, and so forth. So it's a very smart firewall. You'll see more of Perimeter later because it's also got the most complicated networking requirements of anything we've got. Clearwater IMS Core, that does basically all the work, handles all the calls, routes calls from point A to point B, and has all the different components that send your call into the right place. We have a TAS, which provides call services such as forwarding, telephony application server. We have MRF, because sometimes you have to play noises, music on hold, recording, stuff like that. We have SAS, which is a clever log analyzer and viewer, which is necessary to understand all these pieces because we've already got more pieces than we can diagnose without it. MVSC, which collects a bunch of stats for display in a GUI. I'm not even going to talk about all the various standard open source pieces we had. We have DCM, which is there to annoy customers. That's there because the DCM team are going to be in the talk when I give it work. It's actually a license managing software, which is why the customers hate it, because no customer is ever happy when it fails at all and says your software is not licensed. And DM, which is our deployment manager product, which doesn't actually do anything in this deployment, but is going to be subsequently installed. Why am I showing you all this? Mostly so you understand there's a lot of different pieces. Most of those pieces aren't actually all that complicated in and of themselves, but it's not just spinning up a database, it's spinning up a bunch of different pieces that have to talk to one another in fairly standard ways. Mostly in standard ways. So that's going to be simple, right? We're just going to put all the pieces together. It's going to be a nice solid architecture, and we're going to see how it works. And it took 2 days to get Clearwater, which was the IMS part, up and running. What could possibly go wrong? It'll all be fine. I'll have it all done in a week or two, unquote. It took about 3 months, I think. So the rest of the talk really is all about things that went wrong, or things that were difficult, or things that we learned. And the first one is about shipping packets. I should say it's quite possible I'm going to start now assuming all kinds of technical knowledge that you don't have, so do feel free to shout out if you have no idea what I'm talking about. So it turns out that networking is quite hard. It doesn't look like it should be hard, but I've realized over the years that the more I learn about networking, the less a percentage of the networking knowledge that I realize is out there I actually understand. I've now learned quite a lot, as a result of which I realize that I just have no idea of all the stuff that's going on. It's a very frightening subject. So let's talk about our most difficult networking product and then understand what the challenge is. The most difficult piece is Perimeter. So Perimeters are SBC. It acts as a bridge between networks, and it's being a smart firewall, understanding all the protocols between those networks. So it's a telephony-specific firewall. It's on the media path. Now, when you make a phone call, there's signaling and there's media. Signaling is stuff like, I'm hanging up now, I have just pressed key 3. Media is stuff like, well, it's you talking to your mother, basically. It's noises, right? And the media is sent by a whole lot of little packets every 10 or 20 milliseconds. So there's an awful lot of little packets coming through. And those little packets add up to an awful lot of data. Because it's effectively acting as a firewall, it has to handle denial of service attacks. So on the signaling path, you could be facing somebody who's trying to crack your system by sending in SIP invites with, or SIP registers rather, with vast numbers of different randomly generated passwords to do password cracking. We have a lot of problems with that nowadays. And so it has to be able to handle denial of service to line rate. Basically, if they can melt your network, it's not your fault your service doesn't work. But until that point, it's your problem. So this is very difficult. I should say something about interrupts are evil, by the way. Normally with networking, when you send every packet that arrives triggers an interrupt. So basically the kernel gets told, hey, a packet's arrived, do something with it. Hey, a packet's arrived, do something with it. If you're having packets arrive at the rate of several million a second, and you get an interrupt for every packet, your kernel spends its entire time going, a packet's arrived, I'll just say, oh, another packet's arrived, oh, another packet's arrived, and then it all breaks. So you have to try and avoid interrupts or make them less painful. That'll become important later on. So how do we actually make that work? How do you make fast networking work? And there are two basic ideas. This is what you do in OpenStack. I'm not going to say that all this works in Kubernetes, we'll get to that in a minute, but in OpenStack there's two kind of ideas that you can use. The first one is DPDK. So I've mentioned that interrupts are evil. You can't allow packets, you can't allow yourself to be told when every packet arrives because it's too expensive. You can't do all those context switches. So the way that you handle that is you use something that Intel wrote called DPDK. And if effectively you say, I've got this network interface, I'm not going to let the kernel use it at all. I'm going to get in there, get my own hands on it, put my own network drivers on it, and I'm going to have cores that spend their entire time tight looping, pulling packets off it. And if there's nothing on it, they'll just sit there because they're just in a tight loop doing that. And that means I've got a couple of cores that run at 100% all the time, but I can pull packets off much faster, and it doesn't interrupt the other cores that are doing work by random interrupts all over the place. The downside of that is I've just said stuff about kernel and mucking about with drivers, and you can see where this is all going to go, right? So DPDK, necessary in order to handle the rate of packets that we're dealing with. The second solution that you normally have is SRIOV. SRIOV avoids all the layers of SDN. Now normally, I should have got that picture from the life of a packet from KubeCon, but normally when you configure an SDN, when you configure a network interface in a VM or something like that, what normally happens is that network interface is some virtual interface that connects to some other virtual interface that connects to a bridge, that connects to a real interface that connects to a router, that connects to the house that Jack built, and you end up with it jumping through lots of different layers, and there's lots and lots of work involved. You can't afford that work in a really network-heavy application because you just end up burning all the CPU in the stuff below your application, handling all the packets go through because of all the packet hops. You have to just get those packets out onto the wire as fast as you can without anybody touching them. So one way of doing that is that you have a VM that just owns an entire network interface itself. Not a bad way of doing that, frankly. The other way of doing it is to have what's called SRIOV. So this is something that I think it's a Cisco technology, maybe. I'm not 100% sure. Maybe it's Intel. Don't know. No, it's Intel. Certain network devices that you buy that are very expensive will allow you to spin up what are called VFs, which are kind of logical network interfaces. And the way you should think of it is that the VM has direct access to some slice of the NIC, so it can just put stuff onto the wire. So great, we've solved that problem. Something like OpenStack supports SRIOV. You create this kind of virtual slice of a network interface that you hand over to your VM, and the VM sees it as just an interface, and it really is going straight on the wire and is not going through the host at all. So that's how you do these things in VMs. And Kubernetes. Yeah, Kubernetes doesn't do that. So Kubernetes is plug-in based networking with a CNI. The first oh my god, you're joking problem is that it only has one network interface per pod. That's slightly problematic if your application's job is to be the only thing that is on the intersection of two networks. So that's not great. The networking is always, I should maybe say almost always, SDN with packet redirection. So you can take a network device and push it into a container, but that's not generally the way any of the Kubernetes CNI plugins work. Generally, the way they work is that they do some kind of packet redirection, so they'll send it through tunnels and bridges and all the rest of it. And DPDK is just completely out because there's deep black kernel magic going on, and well, you can't normally run containers privileged, or if you do, it's pretty frowned upon. And mucking about in the kernel drivers in a way that break your network interfaces generally will have bad impact in your host. To give you an idea of how much I hate DPDK, after you've installed DPDK on a box, you generally can't see the network interfaces anymore because the kernel doesn't know they're there anymore in some bizarre way that I never really understood. And it is very messy. So that's just not very pretty, is it? So I feel I need a beer now. So we said, let's get the demo working somehow. Let's just somehow get this thing working before I go mad. And we started trying to work through all these different problems and come up with some kind of solution. So just for the demo, what are we going to do for multiple network interfaces? Well, for the multiple network interfaces, we're going to cheat frantically. So the Kubernetes calls the CNI and says, get me a network interface. What we did instead is we used something called Multus that Intel wrote, and there'll be more about the Intel involvement in a little bit, that effectively cheats. So Kubernetes calls the Multus CNI, and the Multus CNI says, yeah, here's an IP address, and that IP address is on the management interface. Under the covers, however, it frantically goes away and creates some more network interfaces as well that it doesn't tell Kubernetes about at all. So you don't have any Kubernetes knowledge of those, and it's all a bit of a hack, but hey, it works. It gets you going. SRIOV. Well, it turns out there are SRIOV plugins for the CNI. We wouldn't want to use it for absolutely everything because not all of our network devices support this, but you can even do this on AWS or on on certain network interfaces. So great, you create your SRIOV VFs and then you push them into the container in a plugin that I wrote in Bash, probably the only CNI plugin written in Bash in history, but but it seemed like it was going to be so simple that was a good idea. Something that I have now recanted of, but it was too late. So you create your SRIOV VFs and you push them into the container and you're done. Great. And you only do that for containers that need them, which only means the ones that need to be on the particular networks in question, because obviously your Grafana GUI, that just doesn't need all this stuff. And if you try and start pushing SRIOV interfaces into it, you'll run out of SRIOV interfaces quite quickly. And DPDK, yeah, work in progress, I think is the thing we should say about that. Intel have come up with a CNI plugin that apparently does DPDK, and that is fantastic, and I'd love to try it, but I haven't had a chance yet. And I don't actually know how to use DPDK, so I need to talk to the guys from the networking team who understand it, because every time I try to understand it and they explain it, my head hurts. But we believe there are answers to DPDK, but it does require some quite deep, complicated stuff going on. Okay, so we just lived without DPDK for the demo in the end. So could we do this in production? Yeah, well, probably we could. SRIOV support exists, multiple network interfaces. The Kubernetes network SIG does have a plan to fix this. 3 weeks ago, apparently, they changed their minds and decided they didn't need to fix it, so we're currently in some entertaining discussions in which ourselves, Intel, Red Hat, and seemingly Cisco, IBM, and Google are arguing against certain other companies. And surely with all those guys agreeing with us, we're going to win this one. But there are entertaining discussions to try and sort that out. DPDK is still just a pain, but like I said, Intel are doing some work on that. So networking is absolutely horrible. It's really, really complicated, and it requires quite a lot of Kubernetes infrastructure changes to get it all working properly. But we can see that in a year or two's time, we'll be able to do this in production, and for now we have hacks that let us do demos. So hooray! Networking turned out not to be as bad as it might have been. I should also say we did get DPDK working in this demo once, but only once. It never worked again. I've never seen it working, but the team in question assured me that once they managed to get a packet through it. Really quickly, yes. So the next thing we kind of started digging into, and this isn't so much an issue for the demo as more generally in production, is this. So 5 nines. So why do we care about 5 nines? So when you call an ambulance, it's better if the call works. Really quite a lot better. I mean, even with the current state of the NHS, it's much better if the call works. It's also better because if the call doesn't work and it's your fault as a telco, you can go to jail. Telco executives don't like going to jail. This is not good. They probably won't go to jail if it's a genuine error and they've done their best and all the rest of it, but they may get fined, but you can't afford to ignore 5 nines reliability. This is the fundamental reason why telco is not just hard, but why the over-the-top guys can do it much better and easier, because they can afford to have 1 call in 1,000 fail, and BT just can't. You buy phone service from BT, it has to be more reliable, and therefore it's going to cost far more. It's a little bit of a digression, which is when I say 5 nines, do you know what? Does anyone know what I mean? Does everyone know what I mean by 5 nines? People are nodding. Maybe. So 99.999% reliability. But we don't actually agree on what that means, and different customers will argue frantically that their definition is the right one. We've been caught out with a few RFPs where they say things like this, don't define them, and then they beat you up because they mean something different. So most people mean 99.999% of the time the service is up. It's much easier if 99.999% of calls work, because then if a call fails immediately, you can just restart. That's fine. Because there's no way you get to 5 nines reliability on a mobile network, because a certain amount of time your call will just be cut off because something will happen to cut your signal off, even though the service might be generally there. So there's a whole lot of stuff. AT&T had the wonderful definition of 5 nines. There was 99.999% availability, except at times when they didn't feel like providing it. So, yeah, usually it's the first, but careful. So, what do you need for 5 nines? Little question, what is the most important thing for 5 nines reliability? It's not beer, but... And you've thought about it for more, that's what you need. The standard way of getting 5 nines nowadays in a telco environment particularly is you spend a lot of money. So everything needs to be redundant. So your power supply, well, you've obviously got 2 of those, and UPSs as well. Your networking, you have 2 independent sets of switches, all cabled in through the back of all your boxes, going out through different cable ducts, because it's very embarrassing when someone puts a back through the cable ducts and cuts out both sets of hoses. You have halon fire extinguishers that won't knock out the electricity. You have very high-grade servers, and you have RAID arrays everywhere, and all the rest of the shenanigans. It costs a fortune. However, we're moving to Kubernetes, and it kind of doesn't work very well in Kubernetes for reasons I'll come to, but it also isn't really what you want to do, because it's not the modern approach. So the modern approach, actually I'm going to jump to the next slide. I should have done in this order. That's one of Google's first server racks. Google used to make the server racks by buying all the components and then sticking them, sometimes with duct tape, onto bits of plywood. And the reason that they did that was, well, it was cheap, right? This was the early days of Google. They had no beautiful blue glowing data centers. So they were going with a model of cheaper hardware, more redundancy rather. Cheaper hardware, more redundancy. Failures happen, deal with it. Every now and again, one of your servers is going to blow up. Your data center fails, whatever. You just design your software so that it doesn't matter. Lots of software techniques, geographic redundancy, pools of stateless servers so one can blow up, replicate state without full consistency. So if you don't have a necessarily fully consistent database, if you've committed your change to one data center but the other data center isn't there, well, that's fine. You just continue working in some possibly marginally degraded way for a bit. You know, maybe some guy lost his config changes, whatever. Doesn't matter. But what you're really doing is trading much tougher software problems for much, much cheaper hardware. And you can actually get much higher reliability, because whatever you do, we had a customer who lost their central office a little while ago because a tornado destroyed the building. There's just nothing you could do. Sometimes that's going to happen, and if you're building central offices in wherever it was, Iowa, on Tornado Alley, or whatever state it was, that's just occasionally going to happen. They were quite pleased. I think they did lose their 5 nines, but they were quite pleased that a few weeks later they'd managed to get something up and running again to start providing service again. But that was the end of their phone system. So now in the virtual world, you might think it's actually even worse than that, because thinking about OpenStack deployment uptime, if you get 3 nines, you're doing pretty well, right? OpenStack, every time you upgrade it, you tend to lose all your service anyway. Whether or not you do that by design, you tend to have problems. You also have lots of software components managing your VMs that can fail, and that you can fat finger config and all the rest of it. So managing 3 nines on OpenStack is doing pretty well. Even if you're running on something solid like AWS, their reliability numbers are not hitting 5 nines. They're, I think, about 4 and a bit nines on their best data centers. And their worst data centers are 3 nines ish, so not very good. Generally, US East seems to be the troublesome child here.
I think they came 5 nines because they released the same
Yes, they.
like S3 for
Yes, they won't have that level of availability for any individual data center, but they'll have that level of availability across multiple data centers, which leads me to my conclusion, which is that you have to run cross cluster. You have to have your application spread geographically, so any one of the data centers can fail. Kubernetes may be more reliable than OpenStack. We just don't have the numbers to know, but frankly, we're not going to get it to 5 nines without spending so much money on it that it's not worth it. So cross cluster, live with it. So those are the two big challenges. There's a kind of slightly more fuzzy one, which is about being cloud native and fitting in with the Kubernetes world and generally being able to deal with all these things and being able to run everything cross-cluster in a nice, clean way. So you've no doubt all seen this. This analogy is great, right up to the point when you realize that cattle are much bigger than cows. But there's the idea of pets versus cattle. So pets are valued for themselves, named and distinguishable, complex and full of features, and looked after when they fail, just like your email server or your laptop. And cattle are valued for what they can do. They're numbered and anonymous. They're only good at one thing, and when they get wrong, you shoot them in the head, bury them, and buy another one. So you really want to be on the cattle end of that spectrum for your applications. You really don't want to be saying, I need to maintain this container, partly because that's not the way container orchestrators expect things to work, partly because it makes your upgrade and so on impossible, and partly because with geographic redundancy, your container may blow up at any moment anyway. If you're taking geographic redundancy seriously, like Netflix do, you probably come across the Simian Army. They've got things like Chaos Monkey and Chaos Gorilla that take out AWS regions periodically and take out servers periodically and so on. So they'll be running, and all of a sudden, live, they will just lose an AWS region because the Simian Gorilla or the Chaos Gorilla decided, we're going to take this region down to make sure everything's okay. And their mindset is, if you can't do it in production, when at random, if that causes you problems, then a real outage would be a real outage, and that's not good enough. So you have to be in the mindset that you can lose anything at any time. So things that take you three days to set up and carefully tune are going to be a problem. So where do we fit on this spectrum? We're kind of there. We're very large, very special, and need quite careful care and attention. I'm pretty sure we have a name. In lots of different ways, which I'll come to. So the first thing is that in telco you come across cluster pairs all the time. The typical requirements are things like you can't change the server IP during a phone call. If you have a server that your phone is talking to, it's got an IP, and that IP needs to still be responding to that call even if the server blows up. You can't use a load balancer to switch over, and you have to keep the call registration state. So when server A blows up, something has to pick it up and know what state your call was in. So how do we deal with this? Well, you can tell from the title, we have cluster pairs. The traditional telco approach, you have 1+1 active standby. You've got internal network heartbeats, so each of them knows when the other one blows up. And internal states continually replicated, so that if you're in the middle of a call, it knows where you are. And then you can take over the IP by using GARP and L2 networking, which you don't really need to know what that is, except you do need to understand that it's not really something that fits in with a cloud environment. So what do we do about cluster pairs for the demo? Well, it's very, very simple. We just ran one of the pair. That worked great. That might not work. That we might get some interesting questions for doing that in production. So yeah, never mind. The simple reality is that if you're in this state running a 1+1 cluster pair, you generally have to put them in different clusters. It's a complete nightmare to set them all up, and that's the only choice you have in the short term. In the longer term, the intention is that we'll move away, so we just don't use cluster pairs. But these are difficult problems to solve without a cluster pair. A cluster pair at least gives you a sensible handle on it all. So that's going to be one issue. The second thing about cloud native is containers are lightweight and fast, right? Well, we've already heard how they're not always lightweight. The reason they're lightweight is there's no boot process scanning the hardware, there's no init daemon, just a single process, and there's little images. Well, let's imagine that we take one of our telco apps and we put it in a container. How many of those things do you think are true? So we've got lots of boot hardware checks where the blasted thing comes up and verifies that this, that, or the other sysctl stupid thing is set and the kernel's got the right parameters and all these things that it has to do on startup. The init daemon comes up and it fires up 8 different processes and 6 different monitoring daemons and God knows what else. And the images are gigabytes in size because, hey, no one cares how big your image is. So that's a bit sad, really. But again, not something that is impossible to fix. But if you start from an existing telco app, it is very hard to deal with. And generally, the conclusion of all this is we have some very loved products. We've got lots of 1+1 pairs, they're very special products. They're 1+1 pairs. They're big, complex products with lots of moving parts, not microservices. State is everywhere, so they're all stateful to some greater or lesser degree. Replacing an instance is a big deal. We've got some of our products are quite cloud native, and then in terms of, well, they're a nice stateless pool and so on, and in order to add something to the stateless pool, I just go into this database and configure some stuff here, and wait, what? No, that's not how stateless pools work. But that mindset creeps into everything because that is how telco applications have worked for years. They also integrate with all kinds of crazy telco data processes, so logging and billing and management. And naturally, those are telco apps that are deployed in some telco network. Great, they're not cloud native and they don't have cloud native type interfaces. And one of my favorite examples is from the diameter interface, where if you do a search of a particular kind, if you don't subsequently do another search of a different kind a little bit later, the database gets changed. It is I mean, how could some sane person make up that interface? I just can't imagine even what the committee meetings were like that caused that interface. So, to be fair, most of this is historical stuff, right? We've got existing applications and we're trying to run them as containers and they just don't quite fit and we're kind of hammering the round pegs into the square holes. So, most of these can be fixed by some combination of changing our products and replacing our products and writing new products that don't behave this way. Last thing I want to say about Kubernetes is we've got various requirements on our orchestration. So there are lots of missing pieces from Kubernetes that we have in OpenStack and that we have needed in OpenStack. And it's an open question whether Kubernetes is going to provide all these as it gradually acquires more and more features and becomes a bit more bloated, or whether they'll push back and say, nah, you don't need this, tough. And then we'll have to live with it and maybe accept lower performance or whatever. So good examples of this are CPU pinning and NUMA affinity. Do people know what NUMA is? Non-uniform memory. So you've got, say, 2 CPUs, each with 8 cores. Each of those CPUs will have its own section of the memory that it owns. If your application is scheduled on both CPUs, then the memory that it is accessing most quickly will switch from one NUMA set to the other. And that means that it'll become less efficient. And that kind of efficiency becomes really unpleasant when you're having to do very fast packet processing. And so we end up having to pin applications to cores so they only use 1/2 of the NUMA memory. OpenStack will allow you to do all that. I won't say anything nice about how easy it is to configure or anything, but it does work and it's got the capabilities that you need. The scheduling algorithm is another issue that we might need to worry about because, well, we've got a bunch of fairly large applications and generally these scheduling algorithms are based around the idea you've got lots of little applications that you can spread out fairly evenly, and it gets much more complicated and inefficient when that's not true. It also gets more complicated and inefficient when you start thinking of things like some of my nodes are special and of SRIOV, and I want to take account of the SRIOV nodes and put all my SRIOV requiring containers onto them, and try not to use them for non-SRIOV containers. But on the other hand, maybe I could when there's a bit of free space, etc. There's a whole bunch of scheduling thinking that could be done there. That's an area actually where OpenStack is a little bit weak too. You can do some manual things, but it's not trivial. IPv6. Kubernetes does not support IPv6. That's kind of terminal, really, because a lot of our customers are running on IPv6 only networks. That is one that the networking SIG is planning to put a fix in for and to enhance Kubernetes to support, but I don't know the timescales when that will happen. And then fast networking. I've already mentioned some of this, but just getting all that fast networking stuff through without lots of kernel privileges and so on. So it's an open question as to when all these features will appear. It's an open question of whether, how many of them we really genuinely need in the new world, although some of them we probably do. And but there's clearly a long way to go in terms of stuff that is needed in Kubernetes to do all those things. The history of how they got added is slightly interesting, and a lot of them were added by Intel, who have been mentioned a few times. The reason for that is that Intel want to sell networking kit, basically. They want to sell all their NICs. Therefore, they want SRIOV to work in every possible environment. So they're willing to throw a few engineers and good ones at doing all the work to fit all this stuff together and make it work, in the expectation that they'll sell more hardware. Similar things are beginning to happen in Kubernetes. Red Hat have got involved in Kubernetes fairly heavily, so have Intel. Huawei are beginning to get involved. All of them have kind of similar motivations about, we want to sell our kit, let's make our kit work in this environment. Oops. So what's the takeaway? Other than that I spend far too much time on Google Images. The first thing, I've spent all this time complaining about how painful it was. What do we actually achieve? We proved that Kubernetes can actually orchestrate our products. We had to do a lot of hammering of round pegs into square holes, but we got it all to work. Telcos absolutely love the idea. This was quite surprising to me. I was expecting some telcos to go, yeah, that's kind of cool. Telcos thought it was awesome and fantastic and ran around waving their arms. We did a video demo for MWC. They thought it was just the greatest thing since sliced bread. It's worth saying that love the idea and are willing to buy it. Totally different concepts. Don't ever confuse them. They love the idea in the sense of they want to come and talk to us and are interested. Maybe none of them will ever buy this stuff. A lot of them won't buy it for years and years and years if they ever do, but it's still been fantastic in terms of having conversations with people with lots of money, because we like people with lots of money. They're our friends, or we'd like them to be. Mostly our applications just work, but there are some of them didn't and required quite a lot of work, and there are lots of things that need to happen before we could possibly go to production. Networking is a massive work in progress. The Kubernetes networking model is just not good enough yet. There's a huge amount of work to be done there. Getting availability right in a cloud environment is hard. It's not necessarily any harder than you might expect. Well, it is harder than you expect for telco environments because we've got higher availability requirements. In principle, doing all the things that we do anyway ought to work in a telco environment, but it's a hard thing to do, and it's hard if you start from where we are. And our existing code is just not remotely cloud native, so there's an awful lot of grunge to be dealt with. But we got it working. I'm pleased about that. What's the future? So Kubernetes is great. I was impressed with Kubernetes. It did do some good stuff, but network is still immature, availability hard, performance is hard, change cloud native architecture is very, very hard. Would we make new products in containers? The answer is yes. We've started writing new products to run in containers. I believe that we're going to be running containers either in container platforms or just in VMs in containers, because it allows us to avoid the horror of we have to package this up to run in VMs in these 10 different environments, and they're all subtly different. It makes it much, much easier to package stuff. So containers are the way forward. We've kind of bought into that. And the very last thing, I do have a video. I'm not going to make you watch it, but I'll quickly describe it. I could actually, I could, and then you can decide whether you watch it. It's some very slick sales guys going on about how fantastically wonderful we are, and some quite nice graphics of, oh look, this is Kubernetes. We delete stuff, and the load keeps going. It takes about 10 minutes. I'm inclined not to run over by 10 minutes unless there's strong view, but if anyone is interested in seeing it, then I'm quite happy to share it or to just let you have a look at my laptop. So, unless there is overwhelming wish to see the demo.
We can put it on the Docker Meetup.
Yeah, absolutely. So, cool. Okay, I'm going to stop.